my colleague asked me to talk about the reactivity. That I have done in last 10 years. And then I figured out understanding reactivity is much more interesting. So I talk about how to correlate the electron spectrum with the reactivity. The first, we start from very basic idea how to understand reactivity, how to optimize the geometry, and so on, and all the things I put in the first section. Talk about the technicals, how to locate the transition state, something else with the Orca. Okay, the understanding of transition state. So, okay, now it's much better. With our starting point is still the transition state theory. That in the transition state theory, one assumes that the reactant A and B pass through a specific geometric arrangement, that is so-called transition state, before decaying to the product C and D. This is a simple picture. And then in the Hammond approximation, the stable molecule like the product and the reactant has correspond to the local minimum of the transition of the potential energy surface. And then the chemical reaction can be renewed as the moving of the nuclei from one local minimum to another with the chemical resistance will be the low energy pathway. And then that's all knowing that is any formula in that way. I think that it just gives you the basics when we talk about the similar things. And then in the quantum mechanics or quantum chemistry, maybe in Orca, they deal with the multi-dimension system as Frank talked about it, but the 3 and minus 6 dimension potential energy surface. And then we can identify the local minimum. I need to add a laser pointer. We have the local minimum. We identify local minimum. We calculate the second derivatives of the energy with respect to the displacement, actually normal coordinate. And then all the second derivatives positive that give rise to the positive frequency. And then for the transition state, as I show here, you have you climb up here in this way. If you think about a parabola, your y equal to ax, and the a is minus. In this case, this is the force constant is this a, and then you divide them, calculate frequency, you get an emergent frequency. And then the transition states correspond to the first order center point. It means only one of these second derivatives is negative. The rest of them are positive. It means you only climb up one here, not two. You can climb one here. And then in the technically, we want to calculate the transition state. Okay, I know how to deal with this now. Okay, this one is error. Actually, locating the transition state is not an easy job. Sometimes you need to spend a lot of time and effort. You need more patience for that. And our suggestion, according to our work, we have several things I can share with you. First things, you need to run a relaxed surface scan. Most of the people have tried these things. So-called, what is relaxed surface scan? We take a so-called key reaction coordinate, we figure out which bond is formed, which bond is break, and then you take the bond distance of this bond. And then you fix the bond distance of them, and then you optimize the geometry of the rest of all the coordinates. Now this is kind of give you the feeling of the transition of the potential energy, so-called mapping the surface, the first step. And then you run the frequency calculations at the highest energy geometry, and then you ideally you can find one mode with emergent frequency, and then you look at this mode. You find out the correct mode that connected your reactant and the product, and then you get a good initial guess for the transition state location. And then at this step, you run the real transition state geometry optimization, but you need to read the essence you get it from. You ask the program and Orca to follow the mode that you really break and then form or connect that mode that really connects your reactant and the product. And then at the next step, you need to run a frequency calculation again to verify whether you go to the right or wrong transition state. Sometimes you get the second order setup point. They have two modes with both have the emergent frequencies. Okay. The first question I want to talk with you is how to identify. How can one identify this reaction coordinate? As I mentioned to you, actually most of the things we just guess, speculate using our chemical intuition. And then the two examples I will discuss with you today is nucleophilic attack of the minor anion attack this carbonyl compound. And then the product you want to form this CC bar, so you can scan the CC bar, right? The distance of this one, you put them in these two molecules, several sweet angstrom, for example, and then you scan the CC bar distance, maybe change by 0.1 angstrom at each step. And then the second reaction I discussed with you is anti-atom transfer by hydroxyl radical. The product is the CH3 alkyl radical and the water. So in this reaction, you will form water. You can scan the OH bar. Okay. In most cases, it works, but in our case, we have some tricky case. We want to identify a kind of we want to enumerate all the possible pathways for a given reaction. In that case, this is one step further. You need to compare the joint structure. I have an example to talk about later. And then once you get a transition state, how do you characterize this is the transition that you want? The first thing is actually if the outcome works terminated normally, so-called, and then the first gradient. The first order derivative is close to zero. You really come to this top point, and then you look at this is judged by depends on completely your chemical intuition. You have to look at this transition state chemically makes sense, and then you look at your output, your frequency, the last step, variation step, frequency calculation, and then you find out one and only one mode with emergent frequency. And then the things we usually did in my lab, we usually look at the emergent frequency that is really connected to the bond, that is really connected to the product and the reactant and product and the I have given these several examples in the following. Okay, let us try to understand this simple reaction. This nucleophilic attack on this carbonyl compound. And then we first run the real surface scan. You can start from either point, from the product or from additional products, from product or from reactant. Our experience tells me sometimes this starting from the products is slightly easier. And because you don't know how to align these two fragments in the proper way sometimes. That is some trick they want to know. And then the input file, as I show you here, for the relapse surface scan, And then most of the things we scan this bound distance, that is between the atom 1 and the atom 0. In our case, is this. I think it's this 60 bar. And then that is we give an example. Actually, we don't need 30 steps. We scan the bound distance, this 60 bar distance from 1.5 angstrom to 5 angstrom in 30 steps. So we have very good potential energy surface. And then we take the highest energy geometry and then calculate the frequency and then ask actually, this is a simple case. You only have one emergent mode. And then ask the program follow the mode. That is our program to start counting everything starting from 0, the first mode. That means we have probably have some emergent frequency. And then we optimize the geometry. And then that is you want to check is look at this kind of things. You have to know that from the vibration spectroscopy. Look at this emergent mode. Okay. But somehow a technical issue I think I have resolved to you. I talked about what the trick we have did and everything. We haven't done any of the other tricks, and as far as I know, if my colleagues did something I don't know. But one thing from the chemistry, as a chemistry, I think our task is not to calculate something. We just want to understand something. And then most of the things how to interpret the data in the literature is compare the so-called barrier heights among different possible reaction pathways and give rise to, and then make a conclusion that this pathway is possible, that pathway is energetically not that favorable. But then, as I mentioned here, the primary goal of computational chemistry is however not to provide numbers, but provide understanding, right? And then, actually, this is to give you the many insights on how to improve your system, how to understand and rationalize the trend of your reaction path. And then, our starting point to understand the reactivity comes starting from the kind of assumption that we believe that chemical reactivity is intimately correlated with the electron structure. So we need to understand the electron structure, and then we can understand reactivity. This is our strategy. Maybe you're better. We start from very simple things, function molecular orbital theory. If you take the second order perturbation, second order perturbation theory, and then you can calculate, formulate the energy change when the two molecules interact with each other. The energy change is somehow described by these three terms. The details you can find in this Jensen's book. And then I just point out several things. The first term, this is represents the repulsion between the occupied orbitals. This is corresponding to our chemical language of the steric effect. And then the second thing is charge interaction between two molecules. And the third term is somehow is the most important things. That is describe the interaction of your occupied molecule orbital on one molecule and interacts with an unoccupied virtual orbital in another molecule. One thing that I believe many people know that interaction of two occupied orbitals has no energy gain for that, because your bounding and anti-bounding orbitals are both occupied. Now you have 4 electrons, both are located in two orbitals, interact with each other, and then you have 4 electrons that occupy the bounding and anti-bounding orbital, and then there's no energy gain from that, from this interaction. That is why the helium diamond does not exist. And then, so that is describe this orbital interaction, and the most function of molecular orbital believes that the interaction between the homo and the LUMA dominant this term. That is this term, and then because of this energy denominator, that's in the understand. And this is a very crude approximation, but it's needed tons of chemical insight from. I will give several examples, and then we start from this thing. Let me first understand the reaction we talked about just now. This nucleophilic cation, carbonyl compound. And then now, this reaction is involving electron transfer from the home of this cyanide anion into the number of this CO pi star. Antibody orbital actually is number of this compound. And then, so that is the first look at it. This electron transfer process is this is electron acceptor orbital at the top layer. And then we look at the numeral. And then you find out which one is the favorite bonding reaction site. This is easy to identify. You compare the weight of carbon and the oxygen. The weight and here the carbon is dominant of this orbital. It can easily overlap with this guy, and then it means that the bond formation at the carbon side is much more favorable and then at the bonding formation at the oxygen. So in this case, we can determine carbon is the reaction site. This is what you have done. You have to understand that. And then this is not things, more cruel things. Yeah. The experimentalists, like you will always mention that once you have very low reactivity for the nucleophilic attack of the CO double bond, one trick you can try is to add some Lewis acid into the system, as I talked about, as I want to analyze with you. What happened there? Usually adding the Lewis acid speed up reaction. This is the experimental findings. And then what we have found out then, the situation is the same, but once you interact Lewis acid calcium here with the carbon, with the CO double bond, presumably interact with the terminal oxygen. And then in this way, you lower you can believe that you lower the energy of the oxygen p orbital, right? Because you increase, formally you can see that is the increase the effective nuclear charge of the oxygen. And by the way, one question before I miss it, I should discuss it here. Sorry. So everybody knows this kind of MO diagram, but one difficulty when you make these things you have to is you don't know which carbon you want to know. Carbon p orbital has higher energy than this guy, or the oxygen p orbital has low energy. This is easy to identify according to the effective nuclear charge or electronegativity. So oxygen has a higher charge nucleus, and so the p orbital has no energy. So one single rule to keep in mind is that I always talk to the students. Your pi orbital has a large weight from the oxygen, and that's the way I show you. And then the antibody orbital has the large weight of the carbon center. This is one thing to keep in mind is lower gets lower, higher gets higher. That is the case there. And once you add the Lewis acid here, you lower the energy of this p orbital, and then so your bonding pi orbital gets more oxygen character, and then your antibonding orbital gets more carbon character. This is the favorite of your bonding, right? You want to form the bond between this carbon and the cyanide, and then simultaneously you add this guy, you add this Lewis acid, you lower the energy of the LUMO, and then you somehow speed up your electron transfer into this pi star orbital. That is what I summarized here. So you have adding the Lewis acid, you lower the energy of the electron accepting orbital, and then speed up the electron transfer. And secondly, you increase the weight of carbon that facilitate bond formation. That is the classical explanation from the functional molecular orbital theory. Okay. So motivated by the success of the Francis molecular orbital theory, we think about how to understand this reaction. Okay, we look at the orbitals, yes, that I show you here. And then the question you immediately want to ask me is this one. So which orbital is relevant to the reaction? Somehow, because in this regard, we strongly suggest people looking at the localized orbitals. And then now you found your players in this game. Then definitely in all these cases you have a 4CH bond that somehow mixed together. In this, when you look at the things like localized molecular orbital, and then you have 3 well-defined sigma CH bond. That's one of these guys. One of these guys is the player of this game, and then another one is that's a singly occupied orbital of this oxidation. That is EAO. And one thing I need to emphasize. You transform the canonic orbital, so that is a canonic orbital that's generated by storing our GPW file. It has the same content with the localized orbital. Between them is just we carry out a unitary transformation, but all the properties are the same. We have the same content of physics. Okay, so we look at this. This is something like you look at the same people, but you from a different perspective. All those things are. We look at the same thing. We don't change anything. Okay, the input I put here, something I think that's quite useful for letting people to know this technique. That's quite useful to interpret the chemical bonding of the molecule. And somehow you need to write a specific input for your Orca dash log. And then this is your input, the name of your GPW files and output GPW files, whatever is here. And for the specific for the CH4 methane, we found the one stronger localized orbital, the carbon bonds, and the four bond centered CH bond that I showed you. And then now we know the player of our games, and then we try to understand the reactivity of them. We did the same things as I talked before. And then for the transition state, I want to point out only two things. For the transition, the CH bond distance is 1.3, 1.2. And then also the bond is, the typical CH bond and the OH bond is close to 1 angstrom somewhere. And then this makes sense because in a transition state, somehow the CH bond tend to be cleaved and the OH bond want to form. And that's okay, this is the geometrical features. That make sense. One thing I don't understand is this one. This CHO is kind of linear arrangement. And then when we look at them, to understand that we analyze the electron structure at the transition state. Sorry. That's what we want. We know at the starting point we have doubly occupied CH bond, one singly occupied kind of oxygen p orbital, and then interact with each other to generate a pair of 3 centered orbital. And now we have three electrons in 2 orbitals, so the bonding partners get doubly occupied and singly occupied. The anti-bonding partner gets singly occupied. And then because of this interaction, this is kind of a covalent interaction, you have some optimal geometry to make that. So the optimal geometry is something kind of a linear arrangement. And then I need to ask you for attention for that, because this kind of orbital interaction give you the fingerprint to differentiate edge atom transfers we discussed here, and the proton coupled electron transfer. We want to make an example to exercise to show this point, but we haven't succeeded to do that. I will come to this point later. This is the CH bond stretching. That makes sense. Okay, now in this specific case, kind of the function molecular orbital does not work. We think about a different way to understand the reactivity. That's what I did in the last 10 years. Since we assume that the chemical reaction can be think about as the electron transfer process that coupled to the bond formation and breakage. It's simply electron transfer process. And in terms of this kind of electron transfer process, there are only two ways to cleave a bond. And one way I call it oxidative cleavage is similar to the organomagnetic electron. The removing, actually this is the removing electron in the bonding orbital. CH bond activation is one of the typical examples for that. You remove one of the CH bond electron, and then you break this CH bond, and then you form the carbon-centered alkyl radical. And then this nucleophilic attack of the carbonyl group is another type. I call it reductive cleavage. You populate the electron into antibonding orbital, also cleave this bond. This is, and based on this thinking, we think about that there are two ways to modulate the reactivity. Once the most important thing we found out is you change the energy gap between the electron donation orbital and the electron accepting orbital. Because this is the transfer process, you make this gap as low as possible and speed up the reaction. And then another thing that's a key point here is overlap. You want to make a bond to compensate the geometric changes in the reaction, and then you want to make a large overlap. That is the function orbital has also said the same thing. So this you want to look at these two players, and then you figure out how they overlap, and then you can generate the initial gas for your geometry, for the transition state geometry. That's the way we thought about it, and then you can determine the reaction side, and then that's what we mentioned. Okay. The idea, following this idea, we think about we need to find the player of our reaction. The way the answer for this question actually we need to first understand the reaction at the molecular level, and then we go to the orbital level. We first you need to identify in your reaction which molecules get reduced or get oxidized, which one is electron acceptor, which one is electron donor. And in most cases, we believe that electrophile acid reductant is electron acceptor, nucleophile base oxidant is electron donor. And then once you know these things, which molecule get reduced, which one is get oxidized, and then you go to one step further to identify your player at the orbital level. Okay, for the electron acceptor, your anti-bonding orbital of the target bond being cleaved is the electron acceptor, electron accepting orbital. And then for the electron donor, the bonding orbital of the target bond being cleaved is electron donation orbital. The example I use all these examples there. The nucleophilic of this reaction. So the CN is definitely nucleophile. Everybody believes that's true. No pair of the carbon, this cyanide anion function as electron donation orbital, and then the pi star orbital of the CO serves the electron accepting orbital. Another case we talked about just now is hydrogen atom transfer of the methane. In this case, clearly hydroxyl radical is electrophile. And then singly occupied the p orbital serves as the electron acceptor, and then the CH sigma bond serves as the electron donation orbital. That is things make it so clear. Okay, based on this assumption or hypothesis, we can understand the things even better. So in the reaction, we want to achieve this electron transfer. In most of cases, something like the CH bond oxidation. CH sigma bond has extremely low energy, as we know. This is very strong bonding in the world. And you want your reaction coordinate is definitely clear. It's elongated CH bond. In this way, you wake the CH bonding orbital because you wake the bonding interaction and increase the energy of the electron donor. And then that's what we talk about. And then you speed up the reaction. And so the barrier actually comes from the geometric distortions to achieve this electron transfer. We have found out is that in most cases actually. And then the nucleophilic is the same thing. So you elongate the CO bond, but now you have your CO pi star electron donor, electron acceptor. This pi star, but you want to elongate it, you lower the energy of that. Right? Because now you have your electron accepting orbital is pi star. Okay. I summarize what we have learned there in recent paper here. And then we look at the chemical reaction in terms of the electron transfer. The first thing is we identify which orbital is electron accepting orbital, which one is the electron donation orbital. And then we think about the transition geometry, the transition state geometry, whatever. That is effective this overlap between them, makes them have the maximum overlap and then achieve the optimal geometry. Okay. And then we somehow need to analyze the jaw structure along the path, along the reaction pathway, and then find out what's going on. In most cases, it's work. And then the things I need to talk about is what we understand before. I suggest we speculate reactivity based on the reactant. This is, in the literature, we have talked about many things about the Bell-Evans-Polanyi Principle. This we use the jaw structure or thermodynamics of the reaction to correlate the thermodynamics with the kinetics. The way we sort of actually this chemically somehow makes sense. The more exothermic reaction we have a lower barrier, and the more endothermic reaction vice versa. And then you will correlate a series of reactions, and then with different driving force, we call it the driving force. And the higher driving force, low barrier. That is most of the case that this simple principle work. But once in my work, we found out that there are many exceptions for that. One typical example is oxygen activation we have talked about. And then most of people drive a car knows this can have all these things have an extremely high driving force, but the reaction is so slow because the problem is that the triplet, the oxygen atom has triplet ground state, and then your product is a singlet, and then this is a spin forbidden reactions. So we have the very strong kinetic barrier to overcome, although this reaction is highly endothermic and exothermic. So once you want to use that principle, you have to check. You have to check carefully. I have an example for that if I have time to cover that. Okay, another thing is the Hammond Postulate. That's also frequently appear in the literature. That is correlated the thermodynamics and with the transition state geometry. If the reaction is strongly endothermic, and then the product, the transition state geometry is very similar to the reactant. And on the another extreme, once the reaction is extremely, the third one, yeah, and extremely endothermic, and then the transition state geometry is very similar to the product. And in this case, yeah, that's what everyone like. This is kind of a postulate. Never prove that that is true. And we found that sometimes yes, it's not that works very well. But I should mention here because pay attention on that. And then this one, finally, I will talk about a lot of vibrational spectroscopy, kinetic isotope effects is one of the isotope effects. Usually we use to identify the you want to prove that the stage bond activation or whatever transformation that involves the hydrogen atom transfer is the rate determined step. This is quite a useful way. The reason behind it, once you change the stage bond in CD, and then the origin comes actually from the different zero-point energy of the CD and the CH bond, as I mentioned, and here and here. Yeah. And that is easy to understand. At the transition state, because your CH bond get cleaved, and then so the force constant gets lower, and then at the CD bond influence gets to higher extent. You can believe that, you can easily think about it that way. Once your transition state, in the transition state, your CH bond or CD bond is completely cleaved. And then in this case, these two lines are overlap to each other because there's no CH bond at all. Force constant is 0. And then that is purely depends on the different zero-point energy of this CD and the CH bond. That is the case here. But this technique has been frequently widely used in identifying the transition state involving the atom transfer, proton transfer, because you change the proton to deuterium and you change the mass by a factor of 2. Now I come to a little bit to our real world. We spend a lot of years to understand the reactivity involving transition metals, and then the transition metals is not an easy case to deal with. Somehow I need to talk about something. First things I need to, you want to understand reactivity, and then our strategy to understand the electron structure. The way to understand the electron structure is to cover this subsection. We have time, yeah. In the most of cases, people talk about the formal oxidation state and the electron structure, physical oxidation state. We prefer this kind of thinking. This is a physical oxidation state is completely related to your DN configuration. By what means you can take to identify how many D electrons in your metal center, and then based on that D electron configuration, you can get the oxidation state of metal center. That is, for example, once you have D4 center, you have iron 5, and then you have D3 center, you have iron 4. So D4 center is iron 4, D3 center is iron 5. Most of the cases they are coincident, but in my cases, most times are different. Because we talk about single electron transfer reactions, especially. People are working here on non-innocent ligands based on, you also have the same problem like that. Computationally, as what I mentioned just now, assigning the physical oxidation state is amount to equivalent to counting the electron, how many D electron in the D-based molecular orbital. That gives rise to DN configuration. Based on that, you can know the oxidation state. The local spin state and on the metal and the ligand can be deduced by how many single occupied orbital based on the ligand and the metal. That is also straightforward. The most last case we have met is the bond is strongly covalent, and in this case, you have a half contribution from the D orbital, half from the metal, and half from the ligand. There's no way to define the oxidation state of the metals and them. And then we try experimentally to design oxidation state. That's also fair as well. I think we have met this kind of system many times. So talk about it. This is a typical things in magnetochemistry. This is a spin coupled, the exchange coupled copper dimer. In this case, we have developed a so-called broken symmetry formula. I think the boss has mentioned it, right? I don't know. And then how to interpret the chemical things. I forgot all the theory, and let us talk about how to look at the electron structure of that. And then we recommended to use so-called corresponding orbital transformation. This one, we transform the alpha and the beta set independently, and then we try to find one from the alpha set, which match the one in the beta set as much as possible. That indicates we calculate the overlap between the orbitals. We try to optimize the overlap between them. The way for this copper dimer, your chemical intuition immediately tells you that the singly occupied electron will occupy d square minus y square orbital, because this is square pyramid, square planar geometry, D9 system. And then one electron on one center based on one copper center, and another one located on another center. This is exactly true. And then the nice thing is the overlap between them can be quantified as the interaction between the stress. The large overlap, the strong exchange interaction. Okay, we'll make all of the things together. This is our trick to understanding electron structure, how to make that picture and diagram. Many people ask me the same problem. The first thing is we need to identify whether your system is spin coupled system like copper dimer, or the pure spin system like the classic Vanna type penta-alkyl iron fluoxo, hexo-alkyl iron ferrous center, or whatever. There are three criteria as far as I know. The first, once you have a spin coupled system, your spin square expectation value is significantly deviated from ideal value. You have extremely large spin contaminant, so-called, but there are real physics behind it. And then if you look at we implemented the so-called unrestricted natural orbital, and then you can find the occupation numbers of this spin coupled pair has at least one pair, that is, one is larger than 0.1, less than 1, and another guy is larger than 1 and less than 1.98. And then the most straightforward way in Orca is to look at the unrestricted corresponding orbital. Let's just I show you the overlap in that case is 0.3, something, okay? Okay, that's why, and then once you differentiate these two things, and then you know how to draw the picture. That's how I will show you later. Firstly, another thing we like to use is so-called quasi-restricted orbital. And then, because in most of cases, it's very hard to identify the SOMO, DOMO, and the virtual, just doubly occupied, singly occupied virtual orbital. And then the kinetic orbital has a trouble with that. I have no time to touch that, but we have designers exercising on that. So transform from canonical orbital to quasi-restricted orbital, some things is you transform your unrestricted hydrophilic solution into the restricted open shell harmonic hydrophilic solution. And then in this case, you can easily identify which orbital is doubly occupied, which orbital is singly occupied, which one is unoccupied. And in this, because in terms of understanding of the things, something is eventually comes at the end is counting the electron numbers on the metal and the center, whatever fragment. And the trick is most trick. In almost all publications, we use the QROs to represent the doubly occupied singly occupied virtual orbitals. Even sometimes we localize, we put the trick together, we localize the QROs. And for the spin coupled pairs, I show you copper dimer, we use the unrestricted corresponding orbitals. The rest of the things I use the same strategy, same trick to do that. One example I want to show that many Göttingen people who work on the similar project on High-Valent iron fluoxo. So you look like the canonical orbital, they are very delocalized, like the normal mode, delocalized everywhere. It's very hard to identify the bonding from them. Once you use the QRO and even localize the QRO a little bit, and then you can find a very good bonding. This iron fluoxo, the exhaust structure you can draw with your pencil is like very similar to the dioxygen. And you look at it, The OPZ orbital inhabits DZ orbital. This is sigma type bonding, and this is anti-bonding orbital, and this is bonding orbital. And then you have two p orbitals, oxygen p orbital, that's inhabit with the d orbital in pi manner, so-called. You form the two pi bonding orbital to anti-bonding pi orbital. And the rest of them, if this guy is dxy is equatorial plane, they interact with your supporting ligand. In this case, we have two sigma donor, so dxy is non-bonding, and the sigma, and the x squared minus y squared sigma anti-bonding. That makes your chemical things very clear, right? That is, and then another thing. Okay, I forgot to mention that. These things, based on this yaw structure, you can figure out there are many pathways that may exist. You look at, once you reduce the metals and then you can get the electron here, many things. And once you oxidize the metals, and then you can come, this electron can come here. But for the iron 4, most of the, this is a strong oxidant and it's actually high-valent center. Okay, so there are many kind of electron acceptor or electron donor in the transition metal involving reactions. That makes things quite difficult. Maybe that's a feature, fantastic feature of the transition metal chemistry. Okay, another thing we may measure, and I don't know if you understand that, the transition metal complex has different spin state. Someone work here is the spin crossover system. And then this indicates the reaction may proceed on different potential energy surface. One example that we studied in literature is iron oxo atomic unit and the reaction with hydrogen. The reactant and the product has the second ground state. But the reaction turns out to proceed on the contact excited surface. Because the second you have strongly the demanding barrier, but the contact surface you have a low barrier, and at this point you cross the surface. And then in this particular reaction, and then the system needs to cross the surface twice. First cross the contact surface, and then you come at this point back to the sector surface. And many things let the Sheng and Hammond Schwartz people to propose so-called two-state reactivity, multi-stable reactivity concept. Okay, I have some time to talk about our work on the search bond activation. Background is, as I talk about, high-valent metals is employed by biology in a series around enzyme to use a high-valent center. For example, somebody talk about the PMMO here, and this is SSMO, soluble methyl oxygenase. And others use the di-iron 4 center. And we talk about today, we are mono-iron high-valent mononuclear iron 4 oxo center. And many things happened in last 10 years. We still did some work here. And then, actually you can imagine, enumerate all the possible pathways. And if you compare the reactant and the product, we will end at 12:30, right? Okay, that's okay. And then we start iron 4, so we end up with iron 3 alcohol something. And this immediately tells you, so this is a true electron transfer process. This is a true electron reduction of the iron center. That indicates true electron oxidation of the alkane stage bond. And then, based on this, that is why I asked you to assign the correctly d electron number, d configuration on the metal center. That is this you use here. And then there are two possible ways. One, you have the concerted pathway, one step transfer to electron, and then you have the stepwise pathway, and then you try. That is the way formulate. That's what I show you here. And then for the stepwise pathway, the first step we call, usually in the literature, we call atrium transfer. And then we form a ferric center bound to hydroferric center and inactive with the carbon radical. And then you rebound these two fragments, you generate the final product. The second step we call rebound. And actually, we combine these two fragments. And your chemical intuition immediately tells you this step is definitely the hard step, is redetermined. Because from here to here, you have extremely high driving force for reaction. Because you're starting from radical and general alcohol. And then, that is, it turns out, every calculation believes that this is redetermined, fit your chemical intuition. And then, once it's struggling a lot, is the concerted pathway. And the barrier for the concerted pathway is extremely high, more than 20 kmol more. And then, so it has discussed in the literature for the last 10, 20 years, 30 years now, because the first mechanism proposed by the Jacobs in 1970s. And so we look at the system. This reaction actually is, when I talk about this true electron oxidation over there of the CH bar. In this reaction, iron 4 center with the electron acceptor. And then make me think rather very unusual is oxygen actually function as a relay to transfer, to effect the electron transfer from the CH bar to iron 4 center. This kind of a proposed mechanism try to tell you, because this substrate cannot directly interact with the iron center because you have the supporting ligand, and that's the steric effect does not allow your substrate to attach to the iron center. And the second question I asked myself at the beginning, and why the consortium mechanism is so high, has so high barrier and low reactivity. And then it turns out it's a simple project, but we end up with a lot of things. We first try to understand the electron structure of reactant. That's what we discussed similar things in the last section. I talk about this is a high-spin iron 4. We have a D4 center things, right? And based on that, we can figure out at least two things. One is the electron acceptor orbital can be these three parts, only can be these three, because the oxygen relay the electron. Well, because all the things happen somewhere pass through the oxygen, and then so the electron acceptor must come from some of these three orbitals that involve the FeO bonding or anti-bonding. Okay, so here after we describe the things that once this pi star orbital serve as electron acceptor, we call this a pi pathway. And then this sigma antibody orbital serve the electron acceptor, we call that the sigma pathway. Based on, and this is the true things. Actually, for this specific species, we can expect two reaction pathway for the CH bond activation. And then based on that, we can easily identify the key reaction coordinate. That's what we want to talk about. Once you know the electron acceptor orbital is all the pi antibonding or pi sigma antibonding with respect to the FeO interaction. So the FeO bond strength elongation should be one of the key coordinates. That's one thing you can identify. That's what I talked about before. At the beginning, once you compare the electron structure, you figure out how the things work, and then you can somehow design your transition state structure. Okay. And another thing I want to point out, let you keep in mind is here. This is iron oxygen sigma antibonding orbital d square. Here we have an intrinsic plane from the p orbital. Here we have intrinsic intrinsic node plane of the p orbital. This is the bonding, anti-bonding, because we have the node plane here between the oxygen p orbital and the d square. Yeah. Because of magic things happens, we analyze the electron structure of transition state. The first things I found out, well, we have the three-centered bonding, anti-bonding orbital similar to what we found out in the method of oxidation by alkyl, by hydroxyl radical. This is a CHO3 bonding, anti-bonding orbital. But in that case, we found that that's a completely radical reaction, right? And then more fascinating things comes from here. We look at carefully of this d square-based orbital. We look at so we change it from anti-bonding to bonding. This is dramatic things we found out then. And then actually our prediction is pretty good. In the Fe bond distance at the transition stage is significantly elongated. At the product we have FU bond distance of 1.65 angstrom. We elongated nearly 0.1 angstrom. Yeah. So things somehow fit our chemical intuition, but some things happen very strange. One is suggest this is a radical reaction, and another thing is this orbital changing from reaction to the transition state, we change from bonding to anti-bonding to bonding. Because now we have only this load plane is due to the intrinsic load plane of the oxygen. So we did that things. We did the so-called random surface scan of this FeO bond distance to recognize how the electron changes along with the FeO bond distance. What we found out is somehow at the 1.65 angstrom, that's clearly iron 4 oxide bond distance. We found out that's typical iron 4 oxide. Nothing special. But once we elongate the Fe bond, we found out actually it's this bonding partner split into a pair. One is iron based, and another is oxygen based. Somehow this is indicate these things. FeO bond homogeneous cleavage. This is actually related to the electron structure of iron 4 because this bond is extremely covalent. Like the HH bond in a dihydrogen molecule, once you cleave the elongate the HH bond for dihydrogen molecule, you will get one carbon atom, one H atom on one side and another H atom on the other side. Example 2 here. We found the same things here because the iron 4 and the O2 minus bond is extremely covalent. So the bond this bond cleavage is different from all the other transition metal donation bonds. And you think about it, if you have, for example, hexaalkyl iron 2, once you try to elongate the FeO bond between the oxygen, between the water and your iron center, you can get the water and iron 2 at the end. No one can tell you can get iron 3 or iron 1 or water radical something like that. But this is the case here. This bond is very covalent. That is what we talk about it. So I understand now the two things I point out here. One thing is in this case, we generate oxygen radical, and this radical interact with the search bond, so we form this so-called picture fingerprint of this atom transfer. No one worked well. Okay, so I mean this one. And then in another one, we formed the iron center that we observe here, but all these two orbitals in virtue comes from the FeO bonding orbital. That is the things there. So this is a short story with this, I feel. So as you expected, maybe your 3 sigma bonding orbital involved to the OH bond, or to the OH
OH sigma bonding orbital, and then your anti-bonding 3-center antibonding orbital involved to the carbon center radical. That all makes sense now. Only the problem is that you have dramatic electrolytic changes during the reaction. This is. Now follow the things we just talked about it now. We have the two kind of the reaction mode that can be evaluated once you look at this nitrogen structure. And the second layer of the complexity arises from this iron 4 oxide usually has the triplet ground state. But the triplet and the quintet ground state usually, as our calculation shows, is usually less than 5 kcal. So the reaction may also take place along on the triplet surface that we talked about. So in total we have two kind of reaction pathway on each surface, and times 2 we have two kind of reaction pathway can follow. In total we have 4 different reaction pathway. Okay, that is I draw the electron transfer diagram here. That is the way we talk about. Just now we talk about this guy. We move an electron from the d square, and then you can also on the quintet surface, and then you can move the electron into this guy, pi star. This is called the pi pathway or the sigma pathway, and then on the quintet triplet surface you have those two as well. In total we have 4, and then we push ourselves really a lot to try to enumerate all the pathways and locate the transition state, and then compare the reactivity between these 4 pathways. That's what we did. We take a very simple system as a mean iron 4 oxide and react with the acid. Eventually in this kind of case, you need to design your transition state geometry. This is not a trivial thing. You need a lot of effort because, as you know, now let us for the triplet sigma, because they have a lower barrier. And then, but once you want to locate the transition state for the quintet pi, because you have a lower state that's available, and Orca trying to find something that's better, because this guy is much better than this guy, of course, there's low energy, right? And then you have to cheat the Orca a little bit, and then try to find that way. So this is most very trivial things. Yes, you need to have a good feeling about your transition state geometry. You run a several step of the scan, and then you can find out. And then I'm going to talk about how to design this in 2 minutes. Okay, and then we found out the quintet sigma pathway is favorable, and the triplet pathway is pi pathway is favorable, and then another pathway. And then in this case, yes, this gives a kind of solid background, solid basis for the true state reactivity that is proposed by Sarson's people. Yeah, and but first things I want to compare. Let us compare the reactivity of the quintet sigma and the triplet pi pathway, and I have several reasons to believe that sigma pathway is more reactive. One reason is that, so we know from our understanding the optimal geometry for the substrate attack is so-called vertical approach. You let the switch bond approach FeO unit on the top, because you will generate oxygen P oxygen radical on the PZ orbital in this direction, right? And then, but once you have a pi pathway, you generate a radical on the OPX or PY orbital. You like the horizontal attack. You want to make this kind of, because your oxygen P orbital is this way. You have this way. You have to approach your substrate in a horizontal way. In the sigma pathway, you have to attach the FeO, attack the FeO unit on the top, from the top. And then, so this is what I draw here. You have different attached pathways. That is what I thought about. You can design you can figure out your geometry of the transition state. but just basis on this kind of electronic understanding. And then, now you know, this kind of optimal geometry cannot be true because you have a very strong stereo effect there. This is a does not allow your substrate to attach on the 90 degree. I mean the FEO's edge, that's like this way, because you have very strong stereo effect on the supporting beam. And then we found, that is true, we found out this FEO edge angle is close to 120. Yeah, that means in the triplet sigma pathway, triplet pi pathway, your optical interaction is very weak because you don't have the optimal geometry. And then you you're subject to a very large stereo effect because you approach the system on, this is your supporting approach on the top. And then, but your sigma pathway approach the system from directly up here. And then you have, so your boundary repulsion as I talked about just now, this corresponds to the steric effect. So your sigma pathway has a small steric component, and then the optimal geometry for your optimal geometry for your optimal interaction. And in these two cases, yes. And then yes, I definitely favor the sigma pathway, of course, right? And then one question we think about at the beginning. Another thing that you have to think about here, once you transfer electron to its pi star orbital, and then you cleave this half pi bond. You have a bonding. Your bonding orbital has occupied by 2 electrons, and then your antibody are already occupied by 1 electron. You have a half pi bond here, and then once you compare with the sigma pathway, you completely break the sigma bond. As you know, the sigma bond is much stronger than the pi bond. This chemically that makes sense. And then we found out, we did the relic surface scan. We found out actually transfer this electron is favored by the half field dishia, because in this case you form the high spin iron 3 set half field dishia stabilize this kind of configuration. So actually, transfer electron to here and to here only difference by 1 kcmol. That's what we talk about. You have larger of the spin polarization on the transition state. That is something people talk about. It's trying to enhance the reactivity. Okay. I have time to still talk about some of our work. Thank you. And recently we extend our work to systematic study reactivity of high-valent center. That is we talk about with you about iron 4, 5, 6, and oxo nitrile compound. And most of, especially electric people know that story. And then we also want to study the actual transfer reactivity of this serious compound. One thing maybe most chemists will believe is that because this reaction is clearly is CH bond oxidation. Once you go to the high oxidation state electron, and then the electron affinity of the high valence, for example, iron 6 is much higher than iron 4. That's clearly right. And then you believe that the reaction will get even faster and faster once you increase the oxidation state on iron center. That's now not to be true. This is what we found out here. Yes, iron 4 also really follow this kind of iron 4, 5 also really follow this trend. Once you increase the oxidation state of iron center, yes, the reactivity gets higher and higher. That makes sense because the electron affinity gets higher and higher. And then once we don't understand clearly is the iron nitrile compound, once we increase the iron oxidation state, we observe the opposite trend. Even the iron 6 we haven't succeeded to locate the transition state, but the barrier is extremely high as we think we can follow that. And so I summarize what we have here, and iron oxo is much more reactive than iron nitrile compound. And then iron oxo compound follows the theory, the reactivity of iron oxo follows the usually chemical trend of the electron affinity. But the nitride does not. We don't know. One thing we did that, this is we first analyzed the driving force. That's the Bell-Evans-Polanyi Principle. Yeah, that's at the beginning. Bell-Evans-Polanyi Principle. Yeah, we plot the reaction driving force, and then the barrier. This is the driving force and the barrier. We found a very good linear combination. Yeah, that means in this particular system, this principle really works. That's not all, as I mentioned at the beginning. And then we go one step further, because we believe hydrogen atom transfer is kind of a special kind of a proton-carbon electron transfer. And then once we know the driving force makes sense, and then we can first we calculate the bond dissociation energy of that OH and H bond, and then we divide this strength into the electron part and the proton part. That is what we thought about. We calculate the so-called electron affinity. This is bond dissociation energy of this guy, and then is equal to the electron affinity of the Fe, high-valent Fe oxonitride compound, and the proton affinity of the one electron reduced form of this guy. That's what we decompose into two parts. And that makes dramatic difference now. And for the iron oxo series, we found out the EA, this is a blue column, that's dominant over the proton affinity. That is these three guys. And then for the nitride, we found the proton affinity dominant over, that is this one, this way, dominant over the EA. So this gives the trend like what we observed in the CH bond activation. Okay, we have published already. Okay, that's made me happy, and then I have time to talk about advice our section. And then now I think I try to convince you of one thing. The CH bond activation by this iron 4 oxo can be interpreted as a metal-mediated radical reaction. This is nothing special, just very similar to a hydroxyl reaction with methane. And then the special case, the feature of this reaction is the covalent bond between the iron oxo, the high-valent iron oxo, masks the radical character of oxy at the beginning of the reaction. So the reaction is something like the first generation can be interpreted with first generation oxyl, and then there's oxyl react with CH bond. And then I think if I explain to you, the quintet sigma pathway is much more efficient than any of the others. It's by far the most efficient pathway is CH bond activation. And the different reactivity of this kind of a high-valent oxo and nitride series have been elegantly correlated with the driving force of the reaction. This kind of thing. Now I come to the first question I raised in this subsection about why the conservative oxygen insertion pathways has so high, has a extremely demanding barrier. The case that if you believe what I'm interpreted at the beginning is right, and then you can immediately follow that in this special case, you want to transfer 2 electrons, you want to accept 2 electrons, and it means you will ask the O2 minus oxo ligand transfer into so-called oxidant species. You have and the open shell. You need the alpha hole and the beta hole on the oxygen atom to get these 2 electrons from the CH bond. And you can imagine that this is a very demanding energetic constant process, and then eventually, yes, that's making this barrier extremely high. And then you can maybe ask the question: how about for example, permanganate reactive with CH? Permanganate reactive with somehow prefer the CH bond activation. Yeah, it's true. It follows the same reaction. high-valent iron, high-valent the metal center follows this kind of presumably very funny reaction, and eventually it's a radical reaction. It generates an oxyl radical in the reaction. But for the permanganate has been published in the literature as well. Follow this kind of thing. Okay. So far so good. And then this is the last talk of this meeting at the summer school. I have to see something about the closing remarks, something like that. First is I strongly suggest all of you people looking at the electron structure. The electrons, we believe that reactivity and the electron structure are intimately linked. Looking at the structure, get the chemical insight into the electron structure, and then that helps you smart thinking. Yeah. And then how to understand, this is a kind of a closing remark for all of the sections in this summer school. And for specific for my section, we propose some different way to think about reactivity. First things we locate the transition state and think about which pathway is more favorable, like most people have done in the literature. And then we analyze the electron structure along the reaction pathway, reactant, transition state, and the even product. And then we figure out the electron transfer diagram. And based on that, we can somehow get an idea how to design the transition state geometry and so on and so forth. And then we can somehow even make a crazy idea to evaluate all the pathways like that. Once we know the electron transfer diagram. And that is, so the way is, I suggest to mapping the electron structure along this reaction trajectory, and then you can somehow visualize how electron transfer takes place and figure out how the reaction takes place. Yeah. Okay, that is bring to the end of my talk, and then I have some time for your question, and then before that, I need. In addition to our organization committee, I have to thank my team. Reason I'm extremely busy among my things is did my co-work. I just talk about something here, and then most of the slides is provided by my team, especially Basket did a lot of work, and then I just designed these exercises and all the things you make for me in class. And then Penta kindly test all the exercises before we come here. And then I have 2 minutes. I use 2 minutes to advise my section, and then I can give you at least 10 minutes for the discussion. You can ask me whatever you want to ask. No. Okay. The first thing, the basic reason for that is I have my team asked me to do so, and then the second very important, I make a jumble with one of my colleagues about which section has more people. Okay, but actually we spend some time squeezing our brain to make some good exercises that you can learn from this kind of a 2 hours practical section. The first is we ask you to look at the HOMO and the NUMO of the CO2 to figure out which central carbon or terminal oxygen is the favorite reaction site for nucleophilic character on the CO2. And then we have designed the exercises ask you to look at the canonical orbital and localized orbital. You can know the trick there, how to look at, for example, ethylene, you can identify pi bond, sigma bond. And then the second exercise is somehow very classical. We ask you to locate the transition state of the CH4 oxidation by hydroxyl radical and calculate kinetic isotope. I think I haven't spent a lot of time on it because I believe the both friend has talked about it a lot. And this is how to use Orca to locate the transition state. And then the third one, we move to a very difficult to understand the bonding of a transition metal complex. That is what we talk about in the second subsection. And also we have some examples to let you Figure use a functional molecular orbital to think about the electrophilic assistance to the nucleophilic chemical. As we discussed, you add the Lewis acid to speed up the nucleophilic chemical onto the carbonyl group. And then I think I have done. I leave the time to you, and then you can ask me any question whatever you want. Thank you.